Thank you everyone for attending, both in presence and online. Okay, so in short, I will talk about this very long titled paper that we are currently writing with a bunch of people in Zurich and in Lisbon, actually. This is a joint venture between my current position at UCL, my previous position at DSF, and the UZH Blockchain Center. And it's about IOTA in particular, which is a DLT, which is different. It's not a blockchain, it's a DLT. It's more similar to Hedera in some ways, but still different from Hedera, and their own solution that they want to implement to generate their own peer-to-peer infrastructure, actually. And in this work, we analyze its network formation model, the peer-to-peer network formation model from a network scientific perspective, and look at its potential vulnerabilities induced by how it is generated. Indeed, the title then, it's heterogeneity and homophily induced vulnerability of a peer-to-peer network formation model. Okay, so first of all, I talked about, as I mentioned, IOTA. So let's first introduce what IOTA is. It's a distributed ledger technology that aims to be a high throughput, low cost, decentralized ledger, and that mainly targets IoT devices as its own members. Okay, so it's mainly intended to act as a communication infrastructure and social infrastructure between IoT devices that can then exchange information and trade between them, this information and their own data that they generate, and integrate basically this IoT infrastructure. It's not a blockchain. It is based on what they call the tangle, which is a directed acyclic graph, so what I will in the future call DAG, which is a data structure where each transaction, each new transaction that is appended to the DAG points to two past transactions that it validates. Okay, so it's basically confirming that these two transactions that have been that are being pointed to are valid, and anybody that appends a new transaction is basically certifying that these other transactions that it's pointing to are valid and should be in the consensus. And the consensus then is kept by following this tangle along the lines. Why did they go for this kind of technology? Well, they wanted to solve the throughput problem that typical blockchains have. Blockchains are linear. They have just one longest chain rule that basically is a bottleneck to the throughput of transactions that they can process. So you have, in the future, you're going to have many different options for a new block that can be appended, but only one ends up being appended to the existing blockchain, to the longest chain. And this is, of course, introducing a lot of costs to getting those transactions validated whenever there is a high demand for appending blocks to the blockchain. Whereas the IOTA tangle, as a DAG, is similar to the hash graph. The Hedera hash graph in this sense, it's more it's a wider architecture. So basically, there is no single line. It's contained in a way that it doesn't diverge, so you don't break consensus because everything stays connected within a reasonable time frame. But the idea is that you can have multiple endpoints depending on where you are in the network, and you're gonna hear about some other part of the network, some other part of this data structure. Maybe you will hear about this transaction just a bit later, but you already know about this transaction because you know about this. Okay, so this is the idea. It's something that makes consensus more probabilistic. It's less. There is not a unique consensus at all times for all the participants in the network, but on average and on the longer term, consensus is achieved. Now there is a problem though. As I mentioned, you may end up having forks here as well. So whenever you have these transactions that point to a previous transaction, but they don't point to transactions that are farther up in this tree, you may end up in a situation where these guys will never learn about these guys, okay? Because these transactions only point to something in this branch, these transactions only point to something in this branch, and unless there is a further transaction down here that points to the two branches, there's no way in which these two branches will communicate, okay? So remember, these are transactions pointing to each other, so basically if I only know about this branch, I will never know about this, and so basically there may be a double spending then, okay? So this problem right now in the first version of IOTA is solved by a coordinator node, which is owned by the IOTA Foundation, and it's basically a super node that has superpowers and has the ability to set milestones in the tangle, so that whenever a situation like this occurs, they will put a transaction here that puts that links to both branches and keeps the tangle contained. Okay. Now this is a different solution. As I mentioned, there are similarities between this kind of architecture and the Hedera in particular. Basically, as I said, this is not a blockchain. This is a growing network of a growing directed acyclical graph. Hedera solved this problem right now by having a permission network of nodes, where only a given number of the council nodes can append transactions, can append blocks in this case, to the hash graph. In this case, anybody can, in principle, append a transaction, but there is a coordinator node, a single node, that is necessary to keep the network in consensus. So slightly different levels of decentralization. In one case, it's decentralized but permissioned, the Hedera case. In another case, it's permissionless but still centralized, in the sense there is a single node that is responsible for keeping consensus. So they want, and this is exactly the kind of thing that the coordinator node does. This is the coordinator node, and at some point it will place a milestone transaction, okay, that keeps the DAG contained. So, of course, this is not great in terms of decentralization. So what they want to achieve is a v2.0 that where they want to do the core decide. Okay, they want to kill the coordinator node. They want to be able to go past it, and basically decentralize this consensus algorithm. Okay, and they want to do so by introducing a reputation mechanism. Okay, so they will introduce. They are already testing this concept of mana, which tokenizes a node reputation, which is accrued through the cross-validation of transactions and by adding value transactions to the tangle. And then basically this will allow most reputable nodes to substitute the coordinator, because then they are the ones that are more likely to append new transactions, and they will try to keep the network contained because they have an interest in doing so, basically. So beyond this consensus thing, there is one particular aspect. And of course, once you kill the coordinator node, basically the state of consensus is broadcast over a peer-to-peer network, okay, just by gossiping. Now, the structure of this peer-to-peer network is actually very important once you have reputable nodes, because you want to avoid at all costs the situation where a reputable node cannot see reliable information from its peers. So basically, you want the reputable nodes to be connected to other reputable nodes at all times, and being able to broadcast this information to as many nodes as possible without being obscured or technically eclipsed from the rest of the network, okay, because they can be excluded, basically. So the other problem that they came up with, that they came up and that they needed to solve, is having an auto-peering mechanism, so an algorithm for generating this peer-to-peer infrastructure that keeps reputable nodes safe from Eclipse attacks. Okay? Eclipse attacks can be run basically as a Sybil attack. So I can set up many nodes at zero cost because this is a permissionless network. I can set up many nodes. I can just surround one very reputable node and exclude it and just pass it false information, okay, and exclude it from communicating with the rest of the network. So basically, I have destroyed the consensus, and I can manipulate the consensus as I want. So how does typical peer-to-peer network formation work? Is through this kind of peer discovery and connection mechanisms. So you first need to know what are your available peers, what are the other nodes that you may connect to, and then you need to get an agreement between the nodes that they are connected and they will start communicating as peers, right? So in this case, a node or a peer, I will interchangeably refer to this, and each node, again, is typically intended to be an IoT device, but it may be a laptop, a computer, whatever, server. It's just a node in the network. And there is a ping-pong mechanism where basically once I have compiled a peer list of potential peers, I will send a request to these potential peers, and they will respond and say, okay, I accept you as a peer, or I don't accept you as a peer, based on a rule that I will discuss in a couple of slides. Okay? So let's go a bit more into the details of how this auto-peering works. So as I said, you want to have a situation where the nodes with high mana, high reputation, are connected to other nodes with high mana, because you want them to be safe from Eclipse attacks. Okay? You want them to be safe from Sybil attacks that just exclude them from the network. Okay? So you want to embed this in the way in which the network is constructed. On the other hand, you still want it to keep it regular. A regular network means that every peer has the same number of connections. Otherwise, it's not a peer-to-peer network anymore. It becomes a server-client network, no? Because if I have a high reputation and I have a large number of connections, and somebody has a very low reputation and only has one connection to me, then I'm in server. Okay? We want to avoid that. So to avoid that, you want a random regular network. You want it to be random so that it's non-predictable, so that it's basically the peers are safe. And you want it to be regular so that it's an actual peer-to-peer network. And you want what is called a homophily along the coordinate that is given by the mana. So the mana is the reputation. You want homophily in the sense that I want people with nodes with similar mana to be connected between themselves. Okay? So let's take this on a line. You have nodes on the mana coordinate, right? And the rule that they will select their potential peers as is this. So basically, they have to be within a multiplicative range of rho from the mana of I. Okay, so mana node I will select its potential peers in this range that ranges from rho times its own mana to the right to 1 over rho times its own mana to the left. Okay, so all these nodes in this range, they are potential neighbors of node I. Now, and rho is a parameter, of course, and there is also another parameter which they call R, which is basically the minimum number of potential neighbors that you want in this set, because if mana becomes too spaced out, you still want to be able to have connections with some neighbors. Okay, so there is a minimum number of connections. In this case, it's 3 for either side. So 3 to the left, 3 to the right, and which means that the node I will have at least 6 potential neighbors. And if there is somebody which is outside of this range, then it can be within the range of rho. Okay. And then once the node has compiled this potential neighbor set, they will start messaging them and say, okay, do you want to be my peer? Do you have slots available? because again, this is a regular network, so you want them to all have the same number of connections. So if I already have all the connections that I have, that I need to have, I will say, no, I cannot have you as my peer. Go ask someone else. Okay. So each node selects their neighbors from this set of nodes, and they go about and query them. In other words, in a more social context, you always hear these things from recommender systems typically, that you are the average of your friends, no? And you can use your friendship network to predict your behavior. In this case, you're the median of your friends. Okay, you're going to have 50% peers that are more reputable than you are, 50% peers that are less reputable than you are. So, in summary, they introduce MANA as a reputation system for nodes within the IOTA network, and the way in which it is obtained is through pledging by whoever generates a value transaction. And it comes in two forms. There is access MANA, which gives access to the network, so being able to send messages over this peer-to-peer network, and consensus MANA, which is the MANA that is necessary to actually maintain consensus, so basically append these transactions, append these messages to the ledger. And the peers establish connections by MANA similarity. Okay, send requests to potential neighbors, and then they get accepted or refused based on how many connections they have available and whether they are in the MANA range that they need to be. Okay, so this is just the protocol. Actually, this may be a good time for questions if there are any about the protocol. I forgot to say at the beginning, I'm not involved in the IOTA development. So if you have questions about the protocol, I can try to answer them, but I'm not one of the developers. What we did is what comes next. So if there are questions about it, please.
So you're saying that two branches may be in a situation where they cannot communicate?
Yeah.
Isn't there like a gossip protocol? So shouldn't they like communication expand exponentially and transaction reach all sides of the network?
So that's true, but if a given portion of the peer-to-peer network only knows about these transactions here,
well, temporarily, because eventually.
But the problem is that it might be forever as well, because remember, this is also the way in which I know that other people exist, because they have the list of potential nodes is also propagated along the tangle. So basically, I can only know that a new node exists in the network by reading the tangle and knowing that they're there. So there is this situation where you may have these kind of forks, and they need to contain it. Also, it may be only temporary as well. No, it may be, but it's slowing down the throughput a lot, because basically, and you may have like double spending attacks and all these sort of things, and then merging consensus again, you have conflicts. Like you may have, since it's not a blockchain, you may have conflicts between these, right? So you cannot merge them, maybe.
Right. And another question, this is more superficial, but the tangle allows you a higher throughput because you're comparing it to a block, right? But
yeah.
What can a tangle achieve that a bigger block cannot in terms of throughput?
It's variable size, basically. It's I may tell you how bigger, no? How much bigger. No? In this case, obviously a bigger block means more memory space,
but
more.
Does the tangle mean the same also?
I mean, you have more transactions that happen in parallel in this case, right? And in the block is kind of like that, but it's a fixed size. So depending on demand, you may still reach the maximum. In this case, you may have it go up and fluctuate. No, it's adaptive in a way. No?
I have two questions. So one is, what happens if I'm on the edge of the arrow and I'm really high M and I don't see anyone above me? So do I need to adjust R?
Yeah, it will connect only to people that is obviously lower than you are, but you're still trying to keep your number of connections as the one that you rate.
The other one is, how much is realistic the IoT objective when there is this reputable node? Because I guess they will need to be reliable enough and process a bit more.
Well,
so
again, not involved in the development, so I cannot speak for IOTA. What I think they have in mind is still something that interacts with people, and at some point it's not just IoT devices communicated between them, right? So you're still going to have some kind of infrastructure and like effectively validating nodes that come up, right? So maybe it's just a Raspberry Pi that it's doing it on its own, no? But your washing machine or well, like a sensor in a truck or whatever, they send messages. So the idea is that you want this like the temperature sensor in a truck that is moving I don't know, frozen goods. You want it to be connected very quickly and in a decentralized fashion over a decentralized network to like whatever like a derivative product that is being currently sold on the market about, I don't know, pork bellies or whatever. Make your own case about it. No, it's having a decentralized. The idea is to have a decentralized network where IoT devices can communicate effectively. Then it's not necessarily all nodes are IoT devices. It may be that you have actual like active nodes.
Because is there a mechanism like in Bitcoin where you can just look at the headers and then have the SPV verification, or because I guess that it's quite complex to be processing and know even where is the tango, right? Because you need to process all the blocks in the end.
Yeah, that's why they have the coordinator right now. No, it sets milestones and it's time stamping as well. No, so it's because you don't know which transaction happened first and so on. It's I mean I don't know all the details, all the technical details about the protocol, because again, not a developer, but it's obviously like there are several complications. They are trying to overcome this by eliminating the necessity for a coordinator node that timestamps and sets milestones to preserve the consensus. But then you had some.
Yeah, you mentioned at one point that consensus happens eventually.
Yeah.
Like probabilistically.
Yeah.
Does that mean that from a use case perspective, I can imagine that limits what use cases IOTA would be useful for?
That depends on how fast the probabilistic is, right?
Exactly.
Yeah.
So if you don't need a high certainty environment, like, okay, the lights are on,
yeah.
maybe. maybe the lights are on, maybe the lights are off. And maybe there's no consequence if the lights are off or the lights are on.
Yeah.
Then this is a good approach.
Yeah.
But as a DLT,
it's like reading the mempool of Bitcoin of Ethereum, no, in a way. It's unconfirmed transactions until in this right now it's until the coordinator node has set a milestone that is below the depth of the transaction that you're interested in.
Yeah.
Once the coordinator node will not be there, it's more or less like you have on a blockchain that you need to wait a bunch of blocks before you are sure that that block is final, no?
Yeah, but is the implication here that the time is longer than what we think of as?
This is very fast.
Yeah?
Like transactions get added very quickly.
Well,
actually, they have a huge problem with spam.
Right.
And that's why they want the access mana to limit message sending over the network.
So you have too much throughput, which lowers the probability of confirmation.
Exactly. Yeah.
Confirmation. Okay.
That's one of the problems. Now you have this thing that can grow like very large, very like. I have a colleague in Zurich that is working exactly on this, doing some agent-based modeling of the growth of this tangle, and he's showing that given that based on the parameters that you put into the model, you may end up with a tangle which is very consistent and very very narrow, or a tangle that just grows like this and never comes back. No, so it's that's why it's probabilistic, but based on like you have control parameters and of course the problem is how do you implement the control parameters in the real implementation.
And is the thinking of the coordinator, is that similar to like a polygon, like a layer 2 when it does a snapshot back to Ethereum?
Not super expert with Polygon, but in this case it's just the IOTA Foundation basically marking the
establishing truth.
Establishing truth at regular intervals, yeah.
May,
So
Also, I have a question. Do you think this is kind of like an equivalent of sharding that they're doing because they're working with neighbors,
in a way.
right? Yeah.
They want to. They want to do sharding on top of this. I'm not an expert on sharding architecture as well, so I know one of the plans for the future of IOTA is also going into sharding. So I guess there is a difference between these two things, but yeah. Okay, so if there are no other questions, we can move on to the simulation and attack. Okay, so as I mentioned, this is where we actually did the work. So we want to, what do we want to do? We want to simulate the formation of the peer-to-peer network, okay, based on the mana and the formation mechanism that they proposed, and see whether these eclipse attacks are actually possible or not, and what kind of eclipse attacks may be possible or not. Okay, so first of all, we need to make some assumptions. First assumption that we make is about reputation. We assume reputation is fat-tailed and features a zip-law rank statistic. Okay, this means basically that your amount of reputation is inversely proportional to your ranking in reputation. So the top, let's say the top guy is has a reputation of 1. The second guy has 1/2, and so on. Okay. And basically, this is the mathematical formula. So basically, the control parameter here is S, the exponent of this rank statistic. Okay, so based on if S is very small, you have a relatively homogeneous mana rank statistics. If S is large, you have a steeper one, which means basically that the top guys have a higher concentration of mana. So let's look at some kind of state space of the model of the network. Okay, so here we have a bunch of visualizations of what this peer-to-peer network looks like in 2 axes. So on the x-axis you have the zip-law exponent S. Okay, so again, low heterogeneity, high heterogeneity in reputation or mana, and then you have rho on the y-axis, which is the tolerance that you have for your neighbor's mana. Okay, so remember this is the range that you can accept neighbors from in mana. Okay, so as you see, when you are very tolerant and there is very little heterogeneity, you are on the top left corner. Basically, the peer-to-peer network is a ball. Okay, it's a very regular network, and like there is no real node that stands out from there, or community of nodes that stands out. The color code is the logarithm of the mana. Okay, so yellow is the top mana node, deep blue is very low mana nodes. Then once you move right in terms of heterogeneity, you start seeing these top mana nodes that start detaching from the rest of the network. Okay, they start becoming their own community. And if you lower tolerance, this is even more clear. No, it's even more pronounced. You end up in a situation where basically the peer-to-peer network becomes a very long aubergine-like network, where you have all your top mana nodes that are clustered around here, and all your low mana nodes that end up being clustered around here. Now, this is kind of intended actually, because remember, this kind of network formation mechanism is all about making sure that high mana nodes are always connected to high mana nodes, and basically there is no chance for me as a Sybil attacker to generate 1,000,000 nodes with 0 mana, surround this guy, and disconnect him from the rest of the network. Okay. However, what we notice from this is that there is another kind of vulnerability here. Is that this network can be cut over here, and it seems pretty easy to do, because I just need to control a very few nodes. In this case, it's just 3 or 4, and I'm able to separate high mana nodes from everybody else. And since everybody else is relying on high mana nodes to get proper information, this may jeopardize the effectiveness of the network. So what we try to do is breaking the network. And we try to do so by identifying a control set of nodes that splits the network in two. And we try to do so in a way that maximizes the damage measure that we design. Okay? And we want to identify basically what is an attacker's best strategy, assuming they don't see the full network, because this is a peer-to-peer network, so I will never see all the network at once. I may be able to gossip a few connections, but I'm not able to know all the network, but I'm able to know where I am in terms of mana, and who am I likely to be connected to based on the network formation protocol that I know, and so I may be able to, that may be enough basically to control a set of nodes that allows me to break consensus. Now, a bit of maths here, but I promise this is probably the only slide with formulas. We define cost and damage. So we want to know how an attack is, how efficient is an attack, and this is basically the ratio of the damage that you can do with the attack over the cost that it costs you to run that attack. And we measure damage and cost in terms of mana, because it makes sense based on how they want to implement the mana, at least from their documentation and how they're testing it. You may be able to lend and borrow mana, so that is kind of a currency in this sense. Okay, so goal is to split the network into two subnetworks, A and B, using a set of nodes that controls the interface between these two subnetworks. The damage is measured by mana and by the fraction of mana that is stuck in the lesser subnetwork. So the fraction of the fraction of mana that is contained in the subnetwork A that contains less mana. So, okay, so let's say I'm able to do a 40-60 split. The damage is 40%. Okay, and the cost is measured by the fraction of mana that I need to control to be able to be at the interface, to be able to control nodes in the set, in the control set, the interface set. Okay, and the efficiency is just the ratio of the two, and then you have the formulas for the amount where capital M is the total mana in the system. Now, of course, as I said, as an attacker, you will never actually know what is the full structure of the peer-to-peer network, but let's assume we do. And let's try to devise a couple of strategies that make sense in this case. So the first one is very simple. It's called we call it a greedy strategy. So you just partition the network into A and B based on the ranking of mana. So you know how each mana is ranked. Each node is ranked in terms of mana. 1 is top mana node. N is the least mana node. I will split AI BI. AI contains all nodes that are above I in terms of mana, in terms of mana ranking. BI contains all nodes that are below I in the mana ranking. And then I do this by trial and error, and then I select the split node that maximizes the ratio of damage and cost. Okay? So this is my greedy strategy, having full information about the network. Based on network science, we can do something a bit different. We can actually look at the structure of the network and try to learn something about it. And one thing that network scientists measure a lot is called betweenness. So betweenness is basically how important is a link in connecting any two nodes in the network. Okay? So it's the number of shortest paths that pass through that link between any two nodes in the network. Okay? And then what I can do is what is called a Graham-Newman network dismantling. So I compute the betweenness of all the links. I remove the link that has the highest betweenness, so that where the most shortest paths pass through. I recalculate the betweenness of all links, and I keep doing this until I end up with two separate networks, two subnetworks. Okay, so this is another strategy that you may have having full information about the network. Now let's look at this betweenness link attack. Forget about the cost, should be cost over damage. Okay, so here you have some violin plots about what is the distribution of your ratio between damage and cost based on our simulation, and on the x-axis you have the heterogeneity of mana. So low heterogeneity, high heterogeneity. And what you see is that when you have very low heterogeneity, it's actually pretty hard to break over the 1, which is what you want. You want to spend less than the damage you make. So it's pretty hard to go above that. But as soon as you have like a decent heterogeneity, in particular s equal 1 is kind of a critical point in the ZIF flow, you have maximal efficiency, okay, which is actually around 4 on average. Okay, so 4 means that I control 10% of the mana, I make 40% damage. Okay, so I'm able to split the network 40-60. So, as I said, these are full information strategies, but we want to inform a blind attack with them. Okay, so I assume that we know all the full structure. Now I will assume that we don't, but what we can do is we can simulate the network, use the betweenness and the greedy strategy, and then see which nodes are most frequently targeted. They're most frequently in the control set, so that I can attempt to control those nodes in a blind situation. Okay, so reiterating, simulate a bunch of random networks, apply the 2 full information strategies based on these simulations, identify the top nodes that are most frequently in the control set, and then once I don't know the structure, I will just go and take the nodes that are in the mana ranking that I know, and target those as to control them. So I will take control of the nodes that are around this I star, which is the most frequently node in the control set, with a range L, and then basically I will measure my efficiency of attack. So let's look at this efficiency. On the left you have a heat map of what it looks like when you use a betweenness informed blind attack. On the right you have the grid informed blind attack. This is an average over multiple simulations. So the lighter the color in general, the better the efficiency of the attack. So what you see in general is that when you have lower tolerance, lower rho, you have higher efficiency. And when you have the ZIF flow around 1, you have, even lower than 1, you have maximum efficiency. Okay, so maximum efficiency in the case of the grid inform is about 10 on average, and of the betweenness one is about 8.5. This was efficiency. Now I'm looking at the cost alone, because of course you may have a very high efficiency, but if you have a very low cost, it's just you're not making a lot of damage. So what I want is the cost to be contained, but also the damage to be very high. So in terms of cost here, you end up having very high cost when you have very high tolerance and very low heterogeneity, as you should expect, and very low cost here, but also very low efficiency, as you remember from the previous plot. What is the difference between the betweenness and the greedy strategies in terms of their attack efficiency? So this is the ratio between the average attack efficiency of the two. It's betweenness over greedy, so it's always less than 1, as we see, or almost always less than 1, barring some statistical error. So basically what this means is that the greedy strategy is generally better at informing your blind attacks. Nonetheless, it's interesting to see this strip here in the middle, which we don't really have a mathematical explanation for. It's just a very interesting fact that basically the betweenness strategy, which is actually doesn't know anything about mana, if you think about it. It's just looking at the network that comes out, sampling it, and trying to figure out based on network structure, on the expected network structure, what would be the best nodes to attack without knowing about mana. It's as efficient as the greedy one in this range of parameters. So I will conclude. Okay, yeah, I think I'm in good time. With a couple of remarks. So what we have shown basically with our simulations is that mana heterogeneity, so the S parameters, as you remember, together with homophily, which is the rho, the tolerance that you have for different mana nodes, leads to a network structure that can actually be efficiently partitioned. And generally speaking, a greedy strategy is superior to the between strategy. However, in specific ranges of parameters, they are equally effective, and this is interesting, like from a conceptual point of view, because it means that actually the network has some property that goes, that converges basically, based on the network formation and the betweenness that comes out of it. And most importantly, in these ranges of parameters, the random regular network structure becomes predictable, which leads to effective blind attacks, even if you don't know the full network. With this, I will conclude. Thank you for your attention, and if there are questions, happy to take them.
No questions of mine.
I have a question, but it's not like about the simulation exactly. It's more about like what can happen. So more generally, the set of nodes that you're taking there is fixed set, a static set of nodes, right? It doesn't change.
Yes.
But in reality, nodes come in and come out.
Yes.
Does this this mana system that has nodes only talk to nodes with similar mana in a dynamic setting, can't that result in some like oligopolistic situations, or making like new nodes highly prone to eclipse attacks?
Yes, that's precisely this. Like this is the kind of oligopoly that that you're mentioning. No, there's very few guys. I mean, of course, the main assumption is that there is already like a very skewed distribution of mana. No? So very few nodes have a lot of mana.
But do nodes with more mana have more control, or they're just talking to each other? But
so this is just the peer-to-peer infrastructure, right? So it's just the communication. First of all, they're not very effective at communicating in this situation, right? Because they're very far from most of the nodes. So they will actually, that's what we're showing in our simulations, basically. You are able to isolate them. So basically, they are very reliable, maybe. They only broadcast through information, but their information is just running between them. And there is very much not a possibility that if you are sitting there, you're getting reliable information. So that's actually a vulnerability of the network, right?
so it's not like by having a lot of mana, you have a lot of stake and therefore a lot of influence. By having a lot of mana, you just...
Based on the way in which you acquire mana, which is anytime you make a transaction, you pledge mana to someone that you think is reputable. So basically, whenever your IoT device makes a transaction, they will give you mana in a way.
So sure, if you have influence, you have mana.
That's kind of like
That's
stake in the sense that it's proof of token ownership in some sense. No, it's just that since I was able to move these tokens, I will pledge this mana. So in a way, it's kind of like stake. I'm not staking effectively. I'm not locking up these tokens somewhere, but I'm showing that I have some skin in the game by pledging, because I'm only allowed to pledge mana because I have some skin in the game.
What is your skin and why do you want more mana if you don't get a monetary reward from having more mana?
That's a fair point. I assume is you like I'm not 100% sure on the answer here. Is mostly probably because you just have a functioning network, and basically there is a network effect of everybody benefiting from this. And since it's relatively low cost to do this, you don't expect the reward to be necessarily very high. You can get basically you get a reward by having it work. I assume that is the rationale, but there may be some actual monetary reward that comes for.
You don't collect transaction fees like a block producer.
Exactly. No.
I'm not sure to fully understand what happened in an attack, but it's a bit of follow-up on this. Is if I can cut part of the network, and I think you assume that it will be a lower mana portion of the network, what can I really do that will be valuable to me? So, because what exactly is the...
Well, I mean...
Can I manipulate transactions? Or what's the kind of...
Maybe a lot of the low mana nodes are actually the devices that you're using, no? Because they are just sending messages. They're not really validating anything, or they are, and maybe you're pledging. They are, whenever they send messages or move value, they pledge their mana to their owner's node, or something like that. So maybe you are excluding a relevant part of the network that is actually using the network, right, from the people that can keep it consistent. So you have this division between validators and users of the network, and you're split. What is kind of the assumption here is that the large number of nodes that sits on this side of the network that gets cut off basically have a lower quality network, but they are actually the majority of the users.
Sure, but what I don't understand is, as an attacker, what's my benefit of creating this eclipse? Is it just to...
Well, you can maybe you're a competitor, or I mean, you're a hacker and you like breaking things, or you want to ransom the network. No, or I mean, maybe you want to double spend from one side to the other.
My question is, so will the incentive be that if you cut it, you get only this specific type of nodes? So it's because as you increase your higher amount of mana, probably more transactions can channel through your nodes, so that you disrupted them a high number of transactions.
True, because even if it's three joins, then for a certain period of time, you become the main validator and the highest trustable node.
That's the point. The point is,
What would be the incentive for the attacker?
the point is that if I sit here, I'm not the top mana owner. I only own like 10% of the mana maybe, but I'm able to detach 40% of the mana from the network, right? So I'm not the top mana owner, I'm not the top validator. But I'm able to control the flow between validators and the users. So I'm actually accruing more power than I should have, right? So that's why the efficiency of the attack has to be bigger than 1. So the ratio between the damage that you make and the cost that you pay. The mana you need to control has to be lower than the mana you're able to separate. In that case, you're for a relatively low price in terms of renting mana from other people or whatever, or accruing your mana based on value transactions, you're able to control a larger fraction of the validating power.
Are you aware how IOTA is looking to solve for this type of attacks?
Well, one thing that came from one of their developers, who is actually the main guy behind the auto-peering mechanism, is that these results are informing their own adaptation of the auto-peering. And one thing that they wanted to look into is perhaps having a variable minimum number of potential peers. So basically adding some noise, such that it's not so deterministic when you are in this kind of situation that you end up in this aubergine, but you may have some connection between here and here that pop up randomly. And basically that makes it much harder and it's a lot more resilient, while not exposing you to a situation where this bunch of nodes can suddenly surround this guy.
So at the beginning you say this is how they prevent civil attacks?
Yeah.
Right? But even like just to prevent someone from creating 1 million nodes and influencing the transactions. But say, so for Bitcoin, you prevent that by attaching influence over consensus of digital identities to the real world wealth that you need to spend in mining.
Yeah.
In proof of stake, it's also the stake is a real world asset.
Yeah.
But here it's an entirely internal asset that you receive by just validating.
Yeah.
So although I don't create a node and immediately have influence, I just can validate for a while, get some mana, and then
yeah. In principle, yes.
It's not a very identity.
They even say that you may be able to borrow mana from other nodes. So I mean, I don't have a position on this. I don't want to make claims. Also, because again, I'm not one of the developers, and they may have actually an answer to this. So I don't want to say something that may be wrong. Yes.
Yeah, I have a question on the homophilic mechanism.
Yeah.
So you said you are the median of your neighbors on the one coordinate, right?
Yeah.
So what exactly is that coordinate? Maybe
Reputation, mana, reputation.
And then would you, and then what is this for in the end? So it has nothing to do with the consensus.
It has to do with the consensus in the sense that you spend, like, based on how much mana you have, you are most likely to be able to append. It's like proof of stake in a way. No? Based on how much stake you have, you are most likely to be in the validator set. You're going to be able to append, like, you have access mana and consensus mana. Access mana is to broadcast messages, so you basically have an allowance of messages that you can send. And consensus mana, you have an allowance of participating in the probabilistic consensus mechanism of IOTA.
Right. And because your value, your mana depends on your neighbor's mana, and your neighbor's mana depend on. So there is a bit of interdependence. How does the
We haven't looked into it yet, but the dynamics of this might be very interesting. Yes. Yeah. The dynamics of this might be very interesting. I mean, the baseline assumption here is this, no? So this is kind of what we expect to have at convergence, right?
Okay.
So I thought that we don't know. Especially because, again, as Juan was saying before, is you have, like, you may have nodes entering and exiting the system. You may have there are all sorts of complications in here, but this is kind of the baseline assumption that we make. We don't put dynamics into the system, but dynamics may be playing a significant role, of course. Especially the dynamics also introduces reshuffles in the peer-to-peer network. This peer-to-peer network is not static; it's reshuffled at randomly regularly intervals. So that also affects, of course, this kind of attack dynamics.
Right. Okay. Thank you very much, Carlo.
Thank you.
No.